In this lecture, I want to discuss the second part of the solar energy and the solar radiation. In this lecture, I will discuss the solar constant and the measurement of the solar radiations. Now, what is the solar constant? The rate at which the solar energy arises at the top of the atmosphere is called the solar constant, ISC, where ISC is equal to 1367 watts per meter square. This is the amount of energy received in unit time on a unit area perpendicular to the sun's direction at the mean distance of the earth from the sun. The solar constant actually varies by plus minus 3% because of the Earth's slightly elliptical orbit around the Sun. The Sun-Earth distance is smaller when the Earth is at perihelion, first week in January, and the larger when the Earth is at the aphelion, that is the first week of July. Some people, when talking about the solar constant, correct for this distance variation and refer to the solar constant as the power per unit area received at the average Earth solar distance of 1 astronomical unit, or AU, which is 149.59787066 million kilometers. There is also another small variation in the solar constant, which is due to a variation in the total luminosity of the sun itself. This variation has been measured by the radiometers aboard several satellites since the late 1970s. It is the most accurately measured from the satellites where the atmospheric effects are absent. The value of the constant is approximately 1.366 kilowatts per square meter. The constant is fairly constant, increasing by only 0.2% at the peak of each 11-year solar cycle. Now the measurement of solar radiation. Active cavity radiometers. This is the one of the instrument by which we can measure the solar radiation. The figure shown the active cavity radiometers. The fundamental or the absolute measurements at standards laboratories use the active cavity radiometers. The solar beam is absorbed on a matte black surface of area A, whose temperature rise is measured and compared with the temperature rise in an identical absorber heated electrically. A radiometer basically absorbs the solar radiation at its sensor, transforms it into the heat, and measures the resulting amount of heat to ascertain the level of solar radiation. In principle, then the alpha AgB star is equal to the P electric. The geometry in such that the absorption alpha is equal to 0.999. Notable uses are of the satellite measurements of the solar constant and for the calibration of the secondary instruments. The methods of the measuring heat include taking out the heat flux as a temperature change, using a water pyroheliometer, a silver disc pyroheliometer, or a bimetallic pyronograph, or as a thermoelectromotive force using a thermoelectric pyroheliometer or a thermoelectric pyrometer. In current operation, types using a thermopile are generally used. Now come to the second instrument, that is pyroheliometer or pyrheliometer. A pyranometer is used to measure the direct solar radiation from the sun and its marginal periphery. To measure the direct solar radiation correctly, its receiving surface must be arranged to be normal to the solar direction. For this reason, the instrument is usually mounted on a sun tracking device called an equatorial mount. Angstrom electrical compensation pyranometer is a reliable instrument used to observe the direct solar radiation and has the long been accepted as a working standard. This instrument has a rectangular aperture, two manganese strip sensors 20 mm by 2 mm by 0.02 mm and several diaphragms to let only the direct sunlight reach to the sensor. The sensor surface is painted optical black and has the uniform absorption characteristics for shortwave radiation. A copper Constantan thermocouple is attached to the ridge of each sensor strip and the thermocouple is connected to a galvanometer. The sensor strips also work as the electric resistors and generate heat when a current flows across them. When the solar irradiance is measured with this type of heliometer, the small shutter on the front face of the cylinder shields one sensor strip from sunlight, allowing it to reach only the other sensor. A temperature difference is therefore produced between the two sensor strips because one absorbs solar radiation and the other does not, and a thermoelectromotive force proportional to this difference induces the current flow through the galvanometer. Then a current is supplied to the cooler sensor strip, the one shaded from the solar radiation, until the pointer in the galvanometer indicates 0, at which point the temperature raised by the solar radiation is compensated by the Joule heat. Now come to the third instrument, that is pyranometer. The pyranometer is used to measure the global solar radiation falling on a horizontal surface. In essence, they have the thermocouple junctions, that is called a thermopile, under a black surface, all under a glass hemisphere. The temperature increase caused by the absorbed insolation produces a calibrated voltage. In practice, they are designed and manufactured with great expertise. The basic measurement is total irradiance on a horizontal surface GTH. Other measurements can be of diffuse radiation only, with direct radiation prevented by an adjustable shade ring. Off beam radiation GB star only that enters a collimating tube continuously tracking the sun's path. Each sensor has a horizontal radiation sensing surface that absorbs solar radiation energy from the whole sky and transforms this energy into the heat. Selected meteorological stations have World Meteorological Office WMO standardized pyranometer with an absolute accuracy is 3%. In essence, they have the thermocouple junctions under a black surface, all under a glass hemisphere. The temperature increase caused by the absorbed insolation produces a calibrated voltage. These are the pyranometers shown in the figure. The figure A is the Keith and Jonen pyranometer with two quartz domes for the standardized global insolation. Figure B in such a pyranometer that is used to measure the global insolation on a solar panel. The figure C is the collimated pyranometers for the measurement of the direct irradiance, and the figure D is the modern online sunshine duration recorder. Now the sunshine recorder, the duration of the bright sunshine in a day is measured by means of the sunshine recorder. The sun's rays are focused by a glass sphere to a point on a curved strip held in a group in spherical bowl mounted concentrically with the sphere. Whenever there is a bright sunshine, the image formed is intensive enough to burn a part on the curved strip throughout the day. As sun moves across the sky, the image moves along the strip. Thus, a burnt trace whose length is proportional to the duration of the sunshine is obtained on the strip. Now, these are the references. Please go through these references from where I made this lecture. Thank you.